Another group of 3. How many groups of 3? Well, it's just our very first problem. It's combinations of A, K to K. Okay? So how do we do this? What must be true for those K-specific arms, think about these 3, to be the set of arms visited during the end trials? And here I'm reminded of Laplace's word. It's just common sense reduced to calculus. We immediately see, but we need to be very clear on what this sentence means. It's not, well, let's see. What must be true for the rat to visit only these arms during end trials? 2 events must happen, A and B. Event A is that each one of the visited arms is among this set of K. So each one of the arms that the rat visited, it's one of these. But that's not sufficient. Each one of these arms was visited. So this may seem to be the same thing, but they're not. One thing is that I only sampled from this set. That's A. But when I sampled at least once each one of them. That's B. Given that I sample from this set, I have to sample each one of the arms. Okay? And that's what makes the problem a little bit tricky, because we need to find the probability of A and B. Well, the probability of A is reasonably straightforward. Each one of the arms visited during the end trials must be in the set of K. So this means that the guy is sampling from the set of K arms. Well, suppose, for example, the K were equal to 3. If the rat samples from this set, the probability that on one trial it samples from the set, in this case would be 3 over 8. In n trials, is 3 over 8 multiplied by 3 over 8 n times. So I'm just generalizing. If I want to make sure that the guy is just sampling from the K arms, well, the number of favorable cases is K. The number of total cases is 8. K over 8 is a probability that I sample from that restricted set. But I want that for n consecutive trials. These are independent, and therefore I just multiply them all, and I get this. Reasonably easy. The hard part is what's the probability that when sampling during n times from this set, I sampled all of them, each one of them, at least once. Because otherwise, I could be sampling from here, but at the end of n trials, I only sampled 2 of them. I was sampled from that set, but I didn't sample each one of them. Then I would have 2 different arms instead of 3 visited. Okay? So this is a tough probability. When you are faced in probability problems with a tough one, think about the opposite. It may be easier. And then go back to the first. So that's another rule of thumb. Sometimes the direct attack is not the best strategy. Go around, try the opposite. So, event B given A, what's the opposite? Well, the opposite is event not B, but given A. What does that mean? Look, if event B means, I'll forget the condition. It's not very important right now. Event B means the rat visited each one of them at least once. Well, what's the opposite? Well, missed one at least. Right? So, the rat missed at least one of the K arms. That's the opposite. This probability turns out to be easier to compute. So, if I figure this out, what I want is not this. I want the opposite. I just subtract it from 1 and I get the result. Okay. Now, we're going to define a random verb. Here we come again. Terminology. Enough to scare lots of people, because A sub j's and X sub j's, there is one good point in this terminology. It forces us to be clear. What exactly are we trying to accomplish? It's abstract. That's the price to pay. So, let's define A sub j, the event. Arm J was not visited on any one of the n trials. The guy missed arm J. Okay? So, our event may be written in this way. Look, if you're trying to figure out the probability that at least one of the arms was missed, well, how can it occur? It can occur because the guy missed either arm 1, or arm 2, or arm 3, or arm 4. So if what we're trying to find is logically equivalent to this, So the probability that at least one of the arms was missed is the probability that arm 1 was missed, or arm 2 was missed, or blah, 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 up to arm k. I'm restricted to k arms here. How do we find this? Well, you probably learned in high school the case where you just have two terms here, probability of A and B. And then sometimes the instructor assigns you the derivation of three terms. I'm going for the general thing and explain what is called the inclusion-exclusion formula. It's awful formula. But if you remember the name, you will never forget it. There is a purpose for this name. It was very carefully chosen. Our mathematician friends are very smart. So they gave it a very nice mnemonic name. You remember this, probability of A or B. You know the formula. It's probability of A plus probability of B minus the intersection. With Venn diagrams, in honor of the British logician, it's pretty intuitive. Notice all the colors did not come up very nicely, but notice the following. I want a probability of A or B. Well, A or B is the entire thing. Okay? So, when I put probability of A, I'm adding the area 1 plus the area 2. When I put the probability of B, I'm adding area 2 plus area 3. But if I stop there, I would have added area 2 twice. I would have counted it one too many times. So, I know that this probability is 1 plus 2 plus 3, because those are the three areas there. But if I go A, I have 1 plus 2. If I go B, I go 2 plus 3. Therefore, I need to subtract 2. That's why we get this subtraction. Now, seeing the problem this way generalizes very easily. Let's go to the third case. The three case. Well, okay. So, now pay attention to the name, please. Here's the formula. Probability of A or B or C, you start by including each one of the probabilities, taken one at a time. It's probability of A, B, and C. You add them. But then you need to exclude, not to overcount, the probability of the pairs. A and B, A and C, B and C. And then you need to include again the probability of the events three at a time. And this is so that you have counted each one of these areas only once. Okay? And this generalizes very nicely. Okay, this is the part that looks awful, but the logic is this. When you have probability of A1 or A2, blah, 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 you add the probabilities of the single events. You include them. How many are they? There are combinations of n, one at a time, which is just n. What about what you do next? Now you're going to exclude. You exclude the pairs. How many are they? Combinations of n, two at a time. Then you're going to include the triplets. Then you exclude the quadruples. And you keep including and excluding, until you reach the number n. The tough part is to realize how many are they, because there is a summation here. How many are they? Look at this pattern. N, one at a time, n, two at a time, n, three at a time. And because I am including and then excluding, the sign is reverse. Okay. So, remember, we're trying to find the opposite of what we want. Our problem is reduced to finding this probability. Okay? So, here's the formula. Probability of one at a time, then exclude two at a time, then include three at a time, and so on. Let's take step by step, one at a time. That will be easy. What's the probability that arm 2, for example, is not visited during n trials? I have k arms. The probability that arm 2 is not visited, this means that I'm constantly sampling from the other arms. Okay? So, it's just k minus 1 over k. Okay? This is on one trial. If I have n trials, it's just the same thing multiplied n times. So, I take advantage of another nice thing in the situation. There is symmetry. And what is true of arm 2 is true of any other arm. Okay? So, here I have my first term. I'm going to build a table. This is the probability that I failed one of the arms n times. How many of these? One is related to the summation, the other to the probability. So I start to build my table slowly. Remember, many steps, each one relatively easy. Now, we need to go to the second term. And I need to hurry a little bit. Okay, what's the in many of these problems,